Picture the heart of the Roman Empire at its peak. Grand aqueducts snake across the landscape, carrying fresh water from distant mountains into the bustling, crowded metropolis. This water, the very lifeblood of the city, then flows through an intricate, hidden network running beneath the streets and into the homes of the wealthy, the public baths, and the fountains. The material that made this possible, the substance that channeled the power of an empire, was lead. It's a name that today sends a shiver down our spines, a word we associate with toxicity and danger. But for the Romans, lead was a miracle metal, malleable, durable, and perfect for shaping the future. This is the story of that profound contradiction, a tale of brilliant engineering wrapped in a silent, creeping peril. We are about to journey deep underground into the workshops and foundries of ancient Rome to uncover exactly how they created the lead pipes that sustained a civilization and may have also contributed to its unraveling. This is more than just a history lesson. It's a detective story, one where the clues are etched into ancient artifacts and the testimony of long-dead writers, pointing toward a mystery that has captivated scholars for centuries. What does it take to build a system that can supply water to over 1 million people? The ambition itself is staggering. The Romans didn't just move water, they mastered it, bending rivers to their will and lifting entire lakes across valleys. And at the very end of that incredible journey, where the water finally met the people, stood the humble lead pipe. Its creation was an art form, a precise and demanding craft. We will discover the ingenious methods Roman plumbers used, from casting the metal in long, sand-lined trenches to carefully soldering the seams with a mixture of lead and tin. They created standardized sizes, they developed specialized tools, and they built utility infrastructure so advanced that parts of it would remain in use for over 1,000 years after the empire's fall. This was a technological triumph that supported unprecedented public health and urban luxury, enabling the famous baths and the countless fountains that defined Roman daily life. Yet, woven into this story of achievement is a thread of unintended consequences. Modern science has given us a perspective the Romans never could have had. We now understand that as water sat in those pipes, especially the soft, acidic water carried by some aqueducts, it slowly leached lead from the walls. This invisible, tasteless poison would have accumulated in the bodies of the Roman people over a lifetime, with potential effects that are still hotly debated by historians and scientists today. Did lead poisoning play a role in the decline of the Roman elite? Could it have affected the mental acuity of its emperors and senators? We will sift through the evidence, separating compelling theories from solid fact, as we explore one of history's great and lingering questions. So join me as we pull back the layers of time. We're going to examine the craft, appreciate the ingenuity, and confront the controversial legacy of how the Romans made lead pipes, the hidden veins of an empire that quenched its thirst for glory with a double-edged sword. To understand the sheer necessity that drove the Romans to build their vast hydraulic network, we must first appreciate the scale of the challenge. Imagine a city of over 1 million inhabitants, the largest the Western world would see for nearly 2 millennia, packed into a space that would feel claustrophobic to us today. This wasn't just a population, it was a constant, roaring demand for water. Every day, this immense city consumed hundreds of millions of gallons. The demand came from every corner of society. There were the monumental public baths, or thermae, which were far more than just places to get clean. They were sprawling social hubs, cultural centers, and gymnasiums, some capable of accommodating thousands of citizens at a time, all requiring a staggering and continuous flow of water into their hot and cold pools. Then, there were the countless public fountains, essential for the daily survival of the vast majority of Romans who lived in cramped apartment blocks without any running water of their own. The wealthy, in their luxurious private villas, expected water to flow into their ornate basins, private latrines, and even into early forms of central heating system. And we cannot forget the spectacles, the naumachia, where they staged massive mock sea battles in flooded arenas, or the constant need to flush out the city's sophisticated sewer system, the cloaca maxima. This was not a luxury, this was the fundamental logistics of urban life on an unprecedented scale. Without a constant, reliable, and massive flow of water, the city of Rome would have literally choked on its own waste and descended into chaos and disease. This insatiable thirst created an engineering problem of monumental proportions, a challenge that became a powerful catalyst for innovation. The aqueducts solved the problem of distance, bringing water from sources dozens of miles away, but that was only half the battle. Once the water reached the city, it had to be distributed with precision. This is where the plumbing system, the fistulae, came into its own, and this is what made lead so profoundly attractive. Why lead? Because it possessed a unique combination of properties that no other commonly available material could match. It was incredibly malleable. Artisans could hammer a sheet of lead into complex shapes with relative ease, forming the tight bends and junctions needed for an urban distribution network. It was also highly durable and resistant to corrosion from water under many conditions, promising a long-lasting infrastructure. Unlike stone or terracotta pipes, which were heavy, brittle, and required meticulous carving and fitting, lead pipes could be fabricated on site, repaired quickly, and adapted to the twisting, turning paths beneath the city street. This malleability allowed for a level of standardization and efficiency that was revolutionary. The Romans could cast pipes in standard diameters, ensuring a predictable flow rate and pressure, a concept that is foundational to modern civil engineering. So, this network of lead pipes became more than just a utility. It was a powerful symbol of Roman civilization itself. The ability to command water, to bring it from distant hills and channel it directly into the heart of the city, was a testament to their power over nature. It was a tangible manifestation of Roman order, engineering prowess, and the Pax Romana, the Roman peace that provided its citizens with comforts and amenities unseen elsewhere in the ancient world. The sound of flowing water in a public fountain was the sound of Roman achievement. The luxury of a bath was a daily reminder of the empire's capability. This societal priority, this driving need to not only sustain but to elevate urban life, is what created the perfect environment for the widespread adoption of lead pipe technology. The engineers and plumbers of Rome weren't just solving a practical problem. They were building the circulatory system for the very heart of an empire, and in doing so, they chose the material that seemed, at the time, to be a gift from the gods, a metal that was easy to work with, lasted for ages, and helped channel the lifeblood of their world. So with this immense demand for water and an engineering culture ready to meet it, the Roman craftsmen needed a material that was up to the task. They found their answer in a heavy, dull gray metal, lead, or as they called it, plumbum. This choice wasn't arbitrary. It was a calculated decision driven by a unique combination of properties that made lead, in their eyes, almost a miracle substance. Its first and perhaps greatest advantage was its incredible abundance within the empire's vast territories. Major mines in places like the Sierra Morena Mountains of Spain, and later in Britain, produced staggering quantities of lead as a byproduct of their relentless search for silver, the real monetary prize. This meant there was a massive, readily available supply of a material that was suddenly very useful for large-scale civic projects, making it a practical and economical choice for building out a city-wide water system. Then, there were the physical properties that made it so perfect for the plumber's art. Lead has a remarkably low melting point, sitting at around 327 degrees Celsius. That's a temperature that could be achieved with a relatively simple wood or charcoal furnace, something a workshop in any Roman town could manage. This low melting point meant it was incredibly energy efficient to cast and recast. A plumber could easily melt down old or damaged pipes and refashion them on site, a level of recycling and flexibility that was simply impossible with stone or baked clay. Compare this to the alternatives. Clay pipes were brittle and prone to cracking with ground shifts or simple impacts. Their joints were also notoriously difficult to make perfectly watertight. Wooden pipes, sometimes used in other cultures, were susceptible to rot, warping, and could impart a terrible taste to the water. Lead, by contrast, was the ultimate problem solver. It was malleable enough to be hammered into custom-fitted joints and shaped around corners, yet once in place, it was durable and long-lasting. A properly installed lead pipe could create a seamless, watertight channel that would last for centuries, as many archaeological finds have proven. This legacy is etched directly into our modern language. The Latin word plumbum gives us our term plumbing, and the man who worked with this metal was a plumbarius, a plumber. It's a direct linguistic thread connecting our world to the workshops of ancient Rome. The very symbol for the element lead on the periodic table, Pb, is an abbreviation of that original Roman name. This wasn't just a minor technological choice. It was so fundamental to their infrastructure that it defined the entire craft for millennia to come. When we think of the Roman water system, we are inherently thinking of a system built on lead, a testament to its perfect alignment with their needs for a workable, reliable, and abundant material to realize their grand hydraulic ambition. Our journey into the heart of this Roman technology begins not in the city, but in the dark, suffocating confines of the mines. To get the lead, they first had to extract its source, a brilliant, metallic-looking ore called galena. The primary mines, like those at Cartagena in Spain, or the later ones in Britain, were places of unimaginable hardship. Miners, often slaves and convicts facing a virtual death sentence, would descend deep into narrow, unstable shafts by the flickering light of oil lamp. They worked in constant peril from tunnel collapses, poor air, and the slow, relentless damage to their lungs from breathing in mineral dust. Using little more than iron picks, hammers, and fire, setting where they would heat the rock face with fire, and then douse it with cold water to cause it to fracture, they painstakingly pried the heavy galena ore from the earth. This raw material, often laced with sparkling veins of silver, was the essential first link in a long and sophisticated industrial chain. Once the ore was hauled to the surface, the real transformation began. The first step was to crush the large chunks of galena into a fine powder. This was often done using heavy stone mortars and pestles, or by large rotary mills operated by manpower or donkeys. This crushing was crucial because it vastly increased the surface area of the ore, making the next stages, melting far more efficient. The powdered ore was then fed into specially constructed furnaces, typically built on hillsides to take advantage of natural wind draft. Inside these furnaces, a chemical miracle took place. The galena, which is lead sulfide, was mixed with charcoal and heated to extremely high temperatures. The charcoal served two vital purposes. First, as a fuel to generate the intense heat needed, and second, as a chemical reducing agent. As it burned, the charcoal would strip the sulfur away from the lead, leaving behind the pure, dense, liquid metal. Achieving and maintaining these temperatures required clever engineering. While some furnaces relied on natural wind, many used manually operated bellows, often made from animal skins, to force a continuous blast of air into the fire. This air blast was the key to raising the heat beyond what a simple fire could produce, allowing the furnace to exceed lead's melting point. As the mixture smoldered, the heavy molten lead, being denser than everything else, would trickle down to the bottom of the furnace and collect in a pit. Meanwhile, the lighter waste material, known as slag, would float to the top and could be skimmed off. But there was an added bonus, a lucrative prize that made the entire enterprise immensely profitable for the Roman state. Galena ore is very often rich in silver. During this smelting process, the silver, which does not oxidize, would separate and remain within the lead. To extract it, Romans employed a further refining technique called cupellation, where the lead was melted in a shallow bone ash-lined hearth called a cupel. A blast of air would oxidize the lead, which would then be absorbed into the cupel, leaving a gleaming button of pure silver behind. This silver was essential for minting the coins that funded the empire, making lead mining a critical support pillar for the entire Roman economy. With the lead now purified and pooled at the bottom of the furnace, it was ready to be cast into a form that was easy to handle and transport. The molten metal would be tapped from the furnace and poured into open stone or clay molds. These molds were designed to produce standardized ingots, known colloquially as pigs because the main channel of the mold, with smaller ingots branching off, resembled a sow feeding her piglets. These pigs weren't just shapeless lumps of metal, they were official products. Many surviving examples are stamped with the name of the mine owner, the emperor, or the reigning consul, marking them as imperial property and allowing their quality and origin to be tracked. This system of standardized casting speaks volumes about the industrial scale of Roman metallurgy. A single pig of lead could weigh well over 100 pounds, and archaeological evidence suggests that the annual output for major mining districts could have reached many thousands of tons. This massive production supplied far more than just pipes. Lead was the plastic of the Roman world, a versatile material used in a staggering array of applications. Beyond the fistulae for water, it was rolled into thin sheets for roofing and flashings to make buildings watertight. It was cast into heavy weights for fishing nets and scales, and into sinister, slinging bullets for the military, often inscribed with taunts for the enemy. It provided linings for coffins, and was even used to write curses on thin sheets that were then rolled up and nailed shut. The sheer volume of production, driven by the dual demands of silver for the treasury and lead for infrastructure, created a material abundance that permeated every level of Roman society. This industrial machine, powered by human suffering in the mines and brilliant chemistry in the smelters, produced the very building blocks that would next be shaped by the hands of the plumber into the veins of the city itself. Now, with a steady supply of lead pigs arriving from the mines, the scene shifts from industrial extraction to meticulous craftsmanship. This is where the plumberius took center stage, the master artisan whose skill transformed raw ingots into the vital arteries of the city's water supply. His workshop was a place of controlled chaos, filled with the rhythmic sounds of metal on metal and the faint, sweet smell of molten lead. Far from a simple laborer, the plumber was a highly skilled technician, possessing a deep understanding of his material and the geometry required to make water flow efficiently. His toolkit, while not vast, was specialized and essential, with each instrument serving a precise purpose in the pipe-making process. First, a heavy mallet was used to break the lead pigs into more manageable pieces. Then, a large flat anvil provided a solid steel surface for shaping. But the most iconic tool was likely the mandrel, a heavy iron stake of various diameters, often anchored firmly into a wooden block. This was the form around which the pipe itself would be created. The plumber would begin by hammering a flattened sheet of lead around the central stake, carefully working the malleable metal until the seam met perfectly. To cut these sheets to size, he used large, powerful shears, capable of slicing through the soft but stubborn metal. Each of these tools was an extension of the craftsman's own hands, and his expertise determined whether a joint would be watertight for centuries or spring a leak within a year. The true test of a plumber's skill, however, came in the joining of these pipes. Creating a continuous run from the main water line to a private villa required seamless connections, and the Romans perfected a soldering technique that was both simple and remarkably effective. They used a solder made from a mixture of lead and tin, which has a lower melting point than pure lead. The plumber would carefully clean the edges of the pipe sections to be joined, then apply this special solder alloy along the seam. Using a charcoal-fired furnace or a small, portable brazier, he would then gently heat the joint. The goal was to melt the solder so it would flow into the seam by capillary action, creating a strong, uniform bond without melting the underlying pipe itself. This required an intimate feel for the behavior of the metals, a delicate balance of heat and timing that separated the novice from the master. Surviving pipes often show these seams, and the quality of the workmanship is still visible today. Some joints are rough and globular, suggesting a rushed job, while others are neat, thin, and nearly invisible, the mark of a true artist. This wasn't just about preventing leaks. It was about maintaining water pressure and ensuring the entire system functioned as an integrated whole. These workshops were not isolated garrets. They were dynamic hubs integrated directly into the pulse of Roman urban construction. A plumberius would typically set up his operation near major building sites or in commercial districts, ready to supply the constant demand for pipes, roofing sheets, and other lead fittings. His work was deeply collaborative. He had to consult closely with the architect to understand the precise layout of a new bath complex or a wealthy patron's villa, ensuring the pipe runs were correctly sized and positioned within the walls and under the floors. More importantly, he worked in concert with the engineers who managed the aqueducts. The plumber needed to understand the water pressure available from a specific aqueduct branch to specify the correct pipe diameter. Too narrow a pipe could restrict flow, while too wide a one was wasteful and could lead to sediment buildup. This collaboration ensured that the grand vision of the aqueduct engineer was successfully translated into a functional reality at the point of delivery. From the monumental to the mundane, the plumber's craft was the critical final link, connecting the awe-inspiring public works to the daily lives of every Roman citizen, turning engineering marvels into tangible comfort. With the raw lead pigs delivered to his workshop, the plumber's first task was to transform that heavy, unrefined block into a workable canvas, a perfectly flat, uniform sheet. This was the foundational stage, where the quality of the entire pipe was determined. To begin, he would use a heavy hammer or an axe to chop off a manageable section of the ingot, placing the smaller chunks into a large, fire-resistant clay pot known as a crucible. This crucible was then nestled into the heart of a charcoal furnace, where intense, carefully managed heat would gradually reduce the solid metal into a shimmering, molten pool. Watching the lead melt required a keen eye. It had to become perfectly fluid without being overheated, as excessive heat could cause the metal to oxidize, creating a brittle, crumbly surface that was useless for crafting. Once the lead reached its liquid state, the plumber, using long iron tongs to protect his hands from the searing heat, would carefully lift the crucible from the furnace. The next step was a dramatic pouring maneuver. He would tip the crucible, sending a stream of dazzling, silvery liquid flowing smoothly onto a large, perfectly flat stone slab or a thick sheet of bronze that served as his casting bed. The molten lead would instantly begin to pool and spread, quickly solidifying upon contact with the cool surface into a dull, gray slab. This initial cast slab was thick and rough, far from the thin sheet needed for a pipe. It now had to be transformed through sheer physical effort. This is where the real craftsmanship began. Using a heavy, broad-faced hammer, the plumber would begin the arduous process of beating the lead, methodically working his way across the entire surface. This wasn't wild pounding, it was a controlled, rhythmic application of force. Each strike served to spread the metal, thinning it out and pushing it toward the edges, much like a baker rolls out dough. The goal was absolute consistency, a sheet with a uniform thickness from one end to the other, with no lumps, no valleys, and no dangerously thin spots. Any imperfection at this stage, any area that was even slightly weaker, would become a critical failure point later. Under the constant pressure of flowing water, a thin spot could eventually fatigue and rupture, causing a major leak that would require tearing up a street or a wall to repair. Some evidence suggests that larger, more industrial operations may have employed a more advanced technique, a form of rolling. Instead of relying solely on hammers, a thick lead slab could have been passed between two heavy, counter-rotating stone or metal cylinders. This would have applied a more even, continuous pressure, producing a sheet of remarkable consistency and at a much faster rate than hand hammering. Whether by the relentless strike of a hammer or the steady squeeze of rollers, this meticulous preparation was what separated a functional pipe from a masterful one. The resulting sheet was the plumber's raw material, a flawless, ductile canvas ready to be wrapped around his iron mandrel and shaped into the durable vein that would carry water for generations. This sheet of lead, now perfectly flat and of uniform thickness, was ready for its transformation into a pipe. The central tool for this remarkable conversion was the mandrel, a solid cylindrical rod, typically made of iron or hardened wood, that acted as the pipe's sole, determining its final diameter and ensuring its structural integrity. The plumber would select a mandrel of the required size. This choice alone spoke volumes about the pipe's ultimate purpose. For narrow pipes feeding a single private residence, a slender iron rod might suffice. For the larger public mains that ran beneath the streets, a much thicker, heavier mandrel, perhaps even anchored into the workshop stone floor, would be necessary. This simple tool was the key to the system's standardization, allowing for the production of pipes with consistent, predictable internal dimensions critical for managing water flow and pressure across the entire city. The process itself was a beautiful blend of brute force and delicate precision. The craftsman would first position his carefully prepared lead sheet over the mandrel. Then, with practiced, deliberate movements, he would begin to wrap the pliable metal around the iron core. This wasn't a simple rolling action. It required a steady hand and a keen eye to ensure the edges of the sheet met along a perfectly straight line, forming a long, clean seam running the entire length of the pipe. Any misalignment here would create a weak point, a potential channel for a future leak. Once the sheet was snugly wrapped, the initial bond had to be formed. The plumber would use a specialized hammer, often with a rounded or convex face, to gently but firmly peen the seam. He wasn't trying to fuse the metal yet. He was mechanically interlocking the edges, pressing and smoothing them together to create a tight, preliminary seal that would hold the pipe's cylindrical form securely around the mandrel. This core technique offered incredible versatility. A single workshop, equipped with a rack of mandrels in a dozen different diameters, could produce the entire spectrum of pipes needed for a complex Roman water system. A thick-walled pipe with an internal diameter as wide as a man's forearm would be cast for a high-pressure main descending from a major aqueduct castellum, capable of moving vast quantities of water. A much narrower pipe, perhaps only the width of 2 fingers, would be perfectly suited for the final branch line feeding a kitchen basin or a small fountain in a courtyard. This adaptability meant that the same fundamental craft, passed down from master to apprentice, could serve the monumental needs of the state and the modest requirements of a private citizen with equal effectiveness. The mandrel method was a triumph of elegant simplicity, allowing a single material to be shaped into a comprehensive and scalable infrastructure solution that could grow and adapt alongside the city it served. But achieving that perfect cylindrical form was only half the battle. The true test of a plumber's artistry, the moment it separated a functional tube from a truly permanent installation, lay in sealing that long, vulnerable seam running the length of the pipe. A poorly sealed seam was a guaranteed future leak, a tiny failure point that could erode over time under the constant pressure of flowing water and eventually cause a catastrophic rupture. To prevent this, the Roman plumbarius employed a sophisticated and visually stunning technique known today as the wipe joint. This process began with the careful application of intense, localized heat. Using a specialized tool, perhaps a long, heavy iron soldering bolt, heated to a glowing red in a portable charcoal brazier, or sometimes the direct and risky application of hot coals themselves, the craftsman would methodically run the heat source along the length of the seam. His goal was not to melt the entire pipe, but to bring just the very edges of the lead sheet to their melting point. This required an incredible sensitivity to the material's behavior. Too little heat and the edges wouldn't fuse, too much, and the pipe wall would sag or develop a hole, rendering the entire length useless. As the heated edges began to soften and shimmer, reaching a semi-liquid state, the plumber would introduce a second tool, a thick, dampened cloth or a pad of pliable leather, often held in his other hand or by an apprentice. This is where the wiping action, which gives the technique its name, came into play. With a swift, confident motion, he would press and smooth the molten edges together, simultaneously wiping away the small amount of excess lead that bubbled up from the fusion. This wasn't a simple cleaning action, it was a forging gesture. The craftsman was physically working the metal, blending the two edges into a single, homogeneous mass. The pressure from the cloth and the precise timing of the wipe forced the liquefied lead from both sides to intermingle and cool as one solid piece, creating a molecular bond that was often as strong as the surrounding pipe wall itself. The result of this masterful technique was a seam that could be both incredibly strong and remarkably discreet. A perfectly executed wipe joint left a smooth, slightly raised bead running along the pipe's length, one that was seamlessly integrated into the body of the pipe. In the finest work, this bead was so skillfully blended that it was nearly invisible to the touch and the eye, a testament to the plumber's control and experience. This was not a skill learned overnight. It demanded an intuitive understanding of thermodynamics, metalwork, and physics. An apprentice might spend years simply observing and practicing on scrap metal before being trusted with a valuable, full-length pipe destined for a senator's home. The master plumber, with his calloused hands and keen eye, could judge the perfect temperature by the color of the metal and the consistency of the molten bead, adjusting his technique on the fly for the specific thickness of the sheet and the ambient temperature of his workshop. The wipe joint was his signature, the definitive mark of quality that ensured the intricate network beneath the city streets would hold its precious cargo of water securely, not for years, but for centuries. But what happens when you need a pipe longer than what a single craftsman can shape on his mandrel, or when you need to navigate a sharp corner or branch off to supply a different building? This is where the Roman plumbers' ingenuity truly shone, in the clever and robust method they developed for joining individual pipe sections together. Once you had a series of these straight, handcrafted pipes, the next challenge was linking them into a continuous, sealed line that could snake through the city's underground channels and within the walls of its structures. The solution was elegant in its simplicity and relied on creating a socketed joint, a design principle so effective that it's still used in modern plumbing today. The process began by modifying the ends of the pipes themselves. On one pipe, the plumbarius would carefully flare the end, hammering it outward to create a widened, bell-shaped opening known as a socket. The end of the next pipe in the line would be left plain, designed to slide neatly into this flared socket. This simple male and female connection was the foundation of the entire joint, providing the physical space and structure for the final, crucial step, the poured lead seal. Creating this permanent, watertight bond was a dramatic and precise operation. First, the plumber would slide the plain end of one pipe into the flared socket of the other, ensuring a snug fit. But a simple push fit wouldn't be enough to withstand the constant pressure of flowing water for long. To lock it in place and create a perfect seal, the craftsman would build a temporary clay dam around the socket joint. This dam acted as a custom mold, encircling the gap between the inner pipe and the outer socket. Then, holding a crucible of glowing, molten lead, the plumber would pour the liquid metal into this clay-enclosed space. You can almost hear the hiss and sizzle as the superheated lead flowed into every crevice, completely filling the annular gap between the two pipes. In a matter of moments, the lead would cool and solidify, fusing the two pipe sections into a single, monolithic unit. The resulting color was incredibly strong, often thicker and more robust than the pipe walls themselves. Once the lead had fully set, the clay mold would be broken away, revealing a solid, gleaming band of metal that bound the pipes together for what could be centuries. The strategic brilliance of this socket and pour technique cannot be overstated. It transformed plumbing from a rigid, inflexible system into something modular and adaptable. This joint was the key that unlocked the incredible complexity of the Roman water network. Because individual pipe sections could be easily connected on site, plumbers were no longer constrained by the length of a single piece. They could run a line for hundreds of feet, connecting pipe after pipe as they went. More importantly, these joints allowed for changes in direction. By using precast elbow sections with sockets at both ends, or by carefully angling the pipes as they were joined, the system could turn corners, traverse uneven ground, and navigate the labyrinthine foundations of large bathhouses and tenement blocks. This modularity also made repairs far more manageable. If a section of pipe was damaged by shifting earth or construction work, a plumber didn't need to replace the entire run. He could simply break the lead collar at a joint, remove the damaged section, and pour a new joint to connect a fresh piece of pipe. This was a maintenance revolution, ensuring the system's longevity and resilience. These pour lead collars were the hidden sinews that bound the entire hydraulic system together. They provided the flexibility and strength needed to build a dynamic, living network that could expand and evolve with the city itself. Every time a new aqueduct was completed, or a new wealthy patron demanded a private water supply, it was these reliable, repeatable joints that enabled the network to grow. They allowed the water to flow not just in a straight line from the hills, but to branch out into 1,000 tiny capillaries, reaching the public fountain in a crowded neighborhood, the cold plunge pool in an imperial bath, and the private cistern in a merchant's villa. The humble poured collar, a simple ring of cooled metal, was the unsung hero of Roman hydraulic engineering, the critical innovation that turned a collection of individual pipes into a truly integrated and enduring system. Of course, a beautifully crafted pipe was only as good as its ability to hold water, and before any section was lowered into a trench or buried within a wall, it had to pass a series of rigorous, practical tests. The Roman plumber couldn't afford to rely on hope. A single leak in a subterranean main could undermine a road, waste a precious resource, and demand a laborious, expensive repair. Their quality control methods were born of necessity, using simple physics and sharp observation to guarantee the integrity of their work. The most straightforward and definitive test was the hydrostatic pressure test. After crafting a length of pipe and sealing its joints, a plumber would cap one end, often with a wooden plug hammered tightly into the socket. Then he would slowly fill the pipe with water from the other end, sometimes using a funnel or a small leather bucket. Once the pipe was full, he would seal the second end, creating a closed system. Now the real examination began. He would watch the sealed seams and poured collars with an eagle's eye, looking for the slightest bead of moisture, the tiniest dark spot of dampness that would betray a pinhole leak or an imperfectly wiped joint. But they didn't just look for active dripping. A more subtle test involved letting the filled pipe sit for hours, sometimes even a full day. If the water level dropped noticeably, it indicated a slow, pervasive leak that might not be immediately visible, a flaw that had to be corrected before the pipe could ever be put into service. For situations where water was impractical or for a quicker preliminary check, plumbers might employ a pneumatic test using air pressure, a method that required a different kind of sensitivity. They would plug both ends of the dry pipe and then attempt to pressurize it, perhaps by blowing air into it through a small tube or by heating the air inside slightly so it expanded. They couldn't measure pounds per square inch like we can, so they relied on their senses. The craftsman would submerge the entire pipe in a trough of water, or more commonly, carefully coat the seams with a thin film of soapy water or even saliva. Then, he would watch intently. If there was a leak, even a microscopic one, the pressurized air inside would escape and form a stream of tiny, telltale bubbles along the seam, pinpointing the exact location of the failure with remarkable accuracy. This technique required a steady hand and a patient eye, but it was incredibly effective for identifying the most common point of failure, the long, vulnerable seam. Alongside these pressure tests, a critical and constant practice was the thorough visual and tactile inspection. Before a pipe was even considered for testing, the plumbarius would run his hands along its entire length, feeling for any roughness, ripples, or dips in the surface that might indicate an area of uneven thickness, a weak spot waiting to happen. He would scrutinize the wiped seam not just for leaks, but for its appearance. A good seam was smooth, with a consistent, slightly raised bead that showed the lead had been properly fused. A bad seam was lumpy, with globules of excess metal, or worse, a visible gap where the heat had been insufficient. He would inspect the poured collars of joined sections, ensuring they were solid, without cracks or shrinkage cavities, and that they formed a complete unbroken ring around the joint. This relentless focus on quality wasn't just about professional pride. It was a reflection of the monumental importance of the entire water distribution system to Roman society. A failure in a private home's pipe was a private nuisance, but a failure in a public main was a civic emergency. It could deprive an entire neighborhood of its water, shut down the operations of a public bath, or undermine the foundation of a major street. The engineers and administrators who managed the aqueducts, the curator aquarum, maintained high standards for the infrastructure under their control. There is evidence that some pipes even bore stamps or inscriptions, not just noting the emperor or consul, but sometimes the name of the plumber or the workshop that made them. This acted as an early form of accountability, a way to trace a faulty product back to its source. In a world without industrial manufacturing codes, this personal responsibility and the craftsman's intimate knowledge of his material were the primary guarantors of quality. The fact that so many of these pipes have been excavated still in perfect, watertight condition after 2,000 years buried in the earth is a powerful testament to the effectiveness of their methods. They prove that the Roman plumber, with his simple tools and profound expertise, achieved a level of durability and reliability that would be the envy of any modern engineer. With the pipes meticulously crafted and tested in the workshop, the next monumental task began, weaving this new metallic vein into the living body of the city itself. This was not a quiet, discreet operation. It was a grand public works project that would have torn up the streets of Rome with a familiar clatter of picks and shovels. The process started at the logical beginning, the endpoints of the great aqueducts. These massive structures delivered water to the city's edge, but it was the distribution tank, or castellum divisorium, that acted as the heart of the entire urban system. From this central hub, the main lead pipes, the fistulae, began their journey, branching out like arteries to feed different city districts. Before a single trench was dug, a team of surveyors and engineers would have plotted the precise course. They used simple but effective tools like the groma, a cross-shaped instrument for sighting straight lines, and the chorbates, a long, water-leveled bench for ensuring a consistent, gentle downhill gradient. This slope was the invisible engine of the entire network. It used gravity to maintain a constant flow and pressure from the high elevation source all the way to a low-lying public fountain. Getting this gradient wrong meant water that was either stagnant or rushed through with destructive force. Once the route was marked, the laborers moved in. Teams of workers, likely slaves and paid laborers, would begin the back-breaking work of excavating trenches along the designated path. These weren't shallow ditches. They were deep enough to protect the pipes from the vibrations of cart traffic and the wear of time, often reaching several feet below the surface. As they dug, they encountered a chaotic subterranean world. They had to navigate the foundations of existing buildings, the buried remains of older structures, and a tangle of other utilities, including the massive stones of the Cloaca Maxima sewer system. This required constant adaptation. The trench might need to swerve unexpectedly, or the pipe layer might have to instruct his crew to dig deeper to pass safely beneath an obstacle. The challenge of varying terrain was constant. If the route crossed a steep valley or needed to be raised to enter a building on a higher level, the pipes couldn't simply be laid in the ground. For these elevated sections, the Romans constructed sturdy support structures. Stone or brick pillars, called pilli, were built at regular intervals, and across them ran continuous brackets or stone capping that cradled the pipe, holding it securely in place as it traversed the open air, a visible testament to the infrastructure snaking through the city. Protecting the pipe once it was in the ground was paramount. While lead is durable, it can be dented by shifting stones or heavy pressure. To shield their precious conduit, Roman workers often built a protective casing right inside the trench. They would line the bottom and sides of the excavation with flat stones or curved ceramic tiles, creating a durable, custom-fitted channel for the pipe to rest in. This stone sleeve acted as a shield, distributing the weight of the backfill soil and the traffic above, and preventing sharp rocks from directly pressing against the soft metal. In some archaeological finds, pipes have been discovered still sitting perfectly within these protective stone cradles, a silent witness to the effectiveness of the technique. After the pipe was carefully lowered into its prepared bed, and the joints were given one final visual check, the trench was carefully refilled and the street surface above was restored, leaving little trace of the complex infrastructure now hidden from view, silently doing its job. This entire operation was a masterpiece of collaboration. The project was overseen by the water administration engineers, the curator aquarum, who ensured the overall plan adhered to the hydraulic principles of flow and pressure. Then the plumbarius and his team took charge on the ground, directing the placement of the pipes he had made, supervising the joining of sections with poured lead collars right in the trench, and verifying the alignment. Meanwhile, the large workforce of laborers handled the strenuous digging and construction of supports and protective casings. This coordination was essential for embedding the system into the urban fabric, from the largest public main to the final connection. For a private home, the process was similar but on a much smaller scale. Once a wealthy citizen obtained a costly license to tap into the public water supply, the plumber would direct the digging of a narrow trench from the main under the street, through the property wall and into the residence. Inside the house, the pipe would be routed within walls or under floors, often held in place by simple metal brackets, until it finally emerged into a courtyard basin or an indoor fountain, bringing the ultimate symbol of Roman luxury and civilization directly into the heart of a private dwelling. Now that we have our pipe securely in the ground, we need to understand where its water actually comes from. All those miles of lead pipework ultimately connected to the most iconic symbol of Roman engineering, the aqueduct. But that connection wasn't a simple, direct hose from the mountains to your home. It was managed with extraordinary precision at a specialized structure that served as the beating heart of the urban water grid, the distribution tank, or castellum aquae. Picture the end of a great aqueduct, like the Aqua Marcia, finally reaching the city after its 50-mile journey. The water didn't just spill out into a lake or a river. Instead, it was channeled into a large, beautifully constructed stone basin, often located at one of the city's highest points to maintain gravity-fed pressure for the entire system. This castellum was far more than a holding tank. It was the central switchboard for the entire metropolis, the place where a single massive flow of water was intelligently divided and dispatched. Inside this tank, the Romans executed a masterful system of distribution. The main aqueduct channel would pour its contents into the basin, where the water would momentarily settle, allowing heavier sediments to sink to the bottom before the clearer water moved forward. Then, at precise points along the walls of the castellum, a series of outlet holes were positioned at different heights. From these holes sprouted the beginning of the lead pipe network. This is where the standardization of pipe sizes became critically important. The largest pipes, with the greatest diameter, were connected to the lowest outlets. These colossal mains were designed to carry the highest volume and pressure, and they were destined for the most demanding public services: the imperial baths, the major fountains, and the industrial district. A medium-sized pipe, branching from a middle outlet, might be routed to supply a public neighborhood or a market square. Finally, the smallest pipes, taking water from the highest, lowest pressure outlets, were reserved for private citizens who had paid for the privilege of a direct connection to their homes. But how did they manage this complex flow? They couldn't just let water gush into every pipe simultaneously. The Romans used a simple yet brilliant system of control: bronze stopcocks and valves. Imagine a heavy, tapered bronze plug, meticulously crafted to fit snugly inside a corresponding bronze sleeve that was soldered directly into the lead pipe right at the outlet of the castellum. By inserting a metal key into the head of this plug and turning it, an attendant could open, close, or partially restrict the flow of water into a specific pipe. This allowed for incredible operational flexibility. If a major pipe downstream needed repair, its stopcock could be fully closed, isolating that section of the network without having to shut down the entire aqueduct. Water could be rationed during a drought by partially closing valves to non-essential lines, prioritizing public fountains over private villas. The discovery of these bronze fittings in archaeological digs shows a sophisticated understanding of hydraulics. They were engineering the flow of water with the same precision a modern technician might use to manage electrical current. This entire arrangement highlights the lead pipe system's role as the indispensable final link in a grand technological chain. The aqueducts were the magnificent long-distance haulers. The castellum was the brilliant logistical brain, but the lead pipes were the capillaries that delivered the lifeblood. Without this flexible, durable, and scalable network, the water would have remained trapped at the city's edge, a monumental achievement with no way to reach its people. The lead pipes translated the raw potential of the aqueduct into tangible reality. They were the element that transformed an engineering marvel into daily comfort, public health, and civic pride, carrying the water from the central distribution point all the way to the final, satisfying splash in a basin. This carefully managed network of pipes was far more than just a passive set of channels. It was a dynamic, living system governed by the fundamental laws of physics. The Romans, whether through rigorous calculation or hard-won intuition, possessed a sophisticated grasp of the hydraulics needed to keep water moving efficiently from the hills into the heart of the city. The entire system's driving force was a single, relentless power: gravity. By sourcing water from distant, elevated springs and maintaining a continuous, gentle downhill slope all the way to the city, the Romans transformed gravity into a constant, reliable source of pressure. This gravitational head, as a modern engineer would call it, is what pushed the water through the aqueduct channels and then onward through the vast underground web of lead pipes. Without any need for mechanical pumps, This simple principle ensured that water could rise to the level of the second floor in an apartment building or shoot upward in an elegant arc from a public fountain. The entire design was a masterclass in harnessing a natural force, creating a silent, invisible engine that never needed fuel and never stopped working. The critical factor in managing this gravity-fed system was the precise control of two interdependent variables, pipe diameter and gradient. Roman engineers understood that these are the primary levers they could pull to control the speed and volume of water delivery. A pipe's diameter acted as a traffic regulator for the flow. A wide pipe offered less resistance, allowing a large volume of water to move at a relatively sedate pace, which is ideal for the high-volume mains feeding a public bath. A narrow pipe, by contrast, would increase the water's velocity, creating a faster, more focused stream perfect for a drinking fountain. The gradient, or the slope of the pipe, was equally critical. It had to be steep enough to maintain a scouring velocity that would keep silt and debris from settling and eventually clogging the pipe, but not so steep that the water would rush through with destructive force, leading to erosion of the soft lead interior or putting unbearable stress on the joint. Evidence suggests they aimed for a remarkably consistent gradient, often around 1 foot of drop for every 1,000 feet of distance, a slope gentle enough to be almost imperceptible but sufficient to keep the water in motion. Of course, operating such an extensive pressurized system came with its own set of physical challenges, and the Romans had to contend with phenomena that still vex modern plumbers today. One of the most dramatic is water hammer, the powerful shock wave that ripples through a pipe when a flow of water is suddenly stopped, like when a stopcock is slammed shut. This surge in pressure creates a loud banging noise and can, over time, fatigue and rupture even the strongest pipe joints. While they may not have understood the complex fluid dynamics, Roman plumbers almost certainly encountered the symptoms. They likely developed practical mitigation strategies, such as advising clients to close valves slowly rather than abruptly, or perhaps even installing small, vented air chambers near problematic valves to cushion the shock. Another common issue was the formation of air pockets. As water flows, it can trap air in high points along the pipe's route. These pockets not only restrict flow, but can also lead to noisy, vibrating pipes and even cause localized corrosion. The solution was likely built right into their installation process. By ensuring that pipes were laid with a continuous, unbroken gradient without any high spots where air could become trapped, and by perhaps incorporating simple air release valves at strategic elevated points, they could systematically bleed trapped air from the system, maintaining a smooth, uninterrupted column of water from source to tap. The true testament to their hydraulic genius lies in the system's sheer reliability and longevity. This was not a fragile network that required constant emergency repairs. It was a robust infrastructure engineered for daily operation over centuries. The standardized pipe diameters, the consistent gradients, and the robust joining techniques all worked in concert to create a balanced and stable flow. Water moved with a steady, predictable force from the castellum divisorium all the way to the final outlet. This hydraulic stability meant that a fountain in a quiet neighborhood plaza would flow with the same dependable rate morning and night, regardless of how many baths were being filled across the city. It's a level of engineering foresight that is deeply impressive. They weren't just building for the moment, they were building for the ages, creating a system whose basic principles of gravity, pressure management, and flow control were so soundly applied that it remained a marvel long after the empire that built it was gone. This hidden, hydraulic harmony was the silent partner to the visible craftsmanship, the invisible force that animated the entire network and made the Roman water system one of the most enduring achievements of the ancient world. The sheer reach of this plumbing technology becomes truly staggering when you pull back from the city of Rome and view the entire empire. This is not a localized innovation. It was a standardized utility system replicated from the sun-scorched markets of North Africa to the damp, misty frontier outposts along Hadrian's Wall in Britain. The Roman Empire, in many ways, was a network of interconnected urban centers, and nearly every one of them required a water supply. To meet this colossal demand, the production of lead pipes transformed into a vast, empire-wide industry. Archaeological finds provide undeniable proof of this scale. In Pompeii, frozen in time by the eruption of Mount Vesuvius, we find lead pipes still in place, snaking through the streets and into the homes of the wealthy, their standardized diameters showing a systematic approach even in a provincial town. The port city of Ostia, Rome's gateway to the world, reveals a similar story, with intricate pipe networks feeding its warehouses, baths, and apartment blocks. And in the distant province of Britannia, at the very edge of the civilized world, the Roman fort at Chester sports its own elaborate lead piping system, a clear statement that Roman amenities were non-negotiable, even for soldiers stationed thousands of miles from the capital. This widespread adoption was made possible by a highly organized and surprisingly standardized manufacturing process. It appears that the basic techniques perfected in Rome were exported along with the legions and colonial administrators. Workshops, or fabrica, specializing in lead work, would spring up near major colonial settlements and legionary fortresses. What's remarkable is the consistency of their output. Excavated pipes from sites across the empire often share common dimensions and construction methods. This wasn't a coincidence, it was a deliberate standardization that speaks to a form of imperial policy, or at least a widely disseminated body of engineering knowledge. A plumber from Carthage could have likely walked into a workshop in Londinium and understood the tools and techniques immediately. This standardization was crucial for logistics and maintenance. It meant that a replacement pipe section or a specific fitting could be produced locally almost anywhere, ensuring the system's resilience and longevity across diverse and distant territories. The economic engine behind this empire-wide network was immense, employing tens of thousands of people in a complex chain of production that stretched from the dark, dangerous mines to the tidy urban workshop. It began with the state-controlled mining operations, which provided the raw material and the silver that funded further imperial expansion. This lead was then transported, often by ship or wagon, to distribution centers. From there, it supplied local plumberii, who manufactured the pipes and fittings for their specific city or region. This created a thriving ecosystem of ancillary trades. Cartwrights were needed to build the wagons for transport, shipwrights to construct the vessels that carried lead pigs across the Mediterranean, and toolmakers to produce the hammers, shears, and mandrels for the workshop. Then, there were the countless laborers, the diggers who excavated the miles of trenches, the masons who built the protective casings and support pillars, and the unskilled workers who mixed the mortar and moved the materials. This was not a niche craft. It was a major sector of the Roman industrial economy, a testament to how a single technological innovation could generate widespread employment and economic activity from one end of the known world to the other. Ultimately, the presence of a lead pipe became a powerful symbol of Roman identity and control. In a remote British villa, a lead pipe feeding a private bath was a clear status symbol, distinguishing the Romanized local elite from the native population. In a frontier fort, it was a matter of military efficiency and morale, providing soldiers with a reliable water source that also reminded them of the comforts of the world they were defending. The technology was a physical manifestation of the Pax Romana, the Roman peace. It represented stability, order, and the benefits of being part of a vast, interconnected civilization. Where the pipes went, Roman culture followed. The network was so deeply embedded that it outlasted the empire's political structures in many places. In some medieval towns, Roman lead pipes remained in use for centuries, their original purpose and makers forgotten, but their function undiminished, a silent, durable legacy of an empire that had once united the world under a common stream of water. So with this incredible network in place, delivering water to millions, we arrive at the central, haunting question of our story. Did the Romans, with all their engineering genius, understand the silent danger flowing through those very pipes? The answer is far from simple and reveals a fascinating tension between observation and scientific understanding. It turns out that a few sharp-eyed individuals in the ancient world did, in fact, sound the alarm. The most prominent voice of caution came from the architect and engineer Vitruvius, writing in the 1st century BCE. In his monumental work, De Architectura, a 10-volume guide to building everything from temples to machines, Vitruvius offers a stunningly prescient warning. When discussing water supplies, he explicitly states that water should be conveyed through earthenware pipes rather than lead ones. His reasoning is breathtakingly astute. He notes that lead workers, those who mined and smelted the metal, had unnaturally pale, sickly complexions. He correctly observed that the fumes and dust from the metal itself seemed to rob these men of their health and vitality. From this, he deduced a logical, if not fully proven, conclusion. If the raw material could cause such visible harm to those who handled it, then water that had been sitting inside a pipe made of that same material could not be wholesome. He championed terracotta pipes as the healthier alternative, arguing that water carried in them maintained its purity and taste. Around a century and a half later, the satirical poet Juvenal adds another piece to the puzzle, though his evidence is more indirect. In his famous satires, while lambasting the corruption and perils of city life, he makes a curious remark about the physical state of the aristocracy. He writes of men who were once sturdy and vigorous, but who now suffer from a debilitating weakness in their hands and feet, a condition that rendered them feeble and impotent. While Juvenal's primary aim was social commentary, not medical diagnosis, his description is strikingly consistent with the peripheral neuropathy, the nerve damage in the extremities, that is a classic symptom of chronic lead poisoning. He wasn't pointing a finger at lead pipes specifically, but he was documenting a suite of physical ailments among the urban elite that align perfectly with what we now know to be the effects of long-term, low-level lead exposure. These men, living in homes with private water connections and dining from lead alloy cooking vessels and wine sweetened with lead-based syrup, were at the highest risk. Juvenal's scornful verses, intended to mock the decadence of his peers, now read like an unwitting clinical report from the past. Yet despite these early warnings, the broader Roman world largely ignored them. Why would such a practical and advanced civilization disregard a potential threat to public health? The crux of the matter lies in the gap between observation and causation. Vitruvius understood that lead was dangerous to those who worked with it directly, but he cannot prove that water, which looked, smelled, and tasted perfectly normal after traveling through a lead pipe, was acting as a slow-acting poison. The mechanism was invisible. There was no sudden, dramatic illness that could be directly traced back to a single sip from a fountain. The effects were cumulative, taking years or even decades to manifest as generalized fatigue, cognitive decline, digestive issues, or infertility. In a world without modern toxicology or epidemiology, it was nearly impossible to connect these common, non-specific ailments to an everyday, essential resource like water. Furthermore, the Roman palate likely became accustomed to the taste. Water that had picked up lead carbonate from the pipes would have a distinctly sweet flavor, a taste that was probably not unpleasant and may have even been desirable, further masking the danger. The powerful economic and practical incentives also worked against any widespread change. Lead was cheap, abundant, and incredibly easy to work with. The entire plumbing industry, from the massive mines in Spain to the thousands of workshops across the empire, was built upon it. Shifting to terracotta on a city-wide scale would have been a logistical and financial nightmare, requiring a complete overhaul of the infrastructure. For the average Roman engineer or city administrator, the immediate visible benefits of a durable, flexible, and easily repaired lead pipe system simply outweighed the vague, unproven theories about a distant health risk. The warnings of a lone architect like Vitruvius were simply no match for the sheer momentum of an established technology that worked so perfectly for its intended purpose. The invisible danger was therefore dismissed, not out of stupidity, but because the evidence available to them was circumstantial at best, while the utility of lead was overwhelmingly, tangibly clear. This sets the stage for a modern scientific debate that is every bit as intense as the ancient one, as we now try to measure the true cost of this technological triumph. So we arrive at the great and contentious modern question, the one that has fueled scholarly debate for decades. Just how toxic was this remarkable water system in reality? The answer is far more complex than a simple yes or no. and it hinges on a crucial, often overlooked factor that lay not in the pipes themselves, but in the very water they carried. The surprising hero in this story might be water hardness. Many of Rome's most important water sources, like the Aqua Marcia, originated in limestone-rich mountainous regions. This meant the water was naturally hard, saturated with dissolved calcium carbonate and other minerals. When this mineral-rich water flowed through the lead pipes, a fascinating chemical process occurred over time. The calcium carbonate would gradually precipitate out of the water, forming a dense, rock-like crust on the interior walls of the pipe. This wasn't a thin film, it was a substantial protective lining known as a sinter deposit. This layer acted as a physical barrier, effectively sealing the toxic lead away from the flowing water. In many ways, the Romans inadvertently created a self-protecting system. Once this sinter coating was fully established, which should take a few years, the water had very little direct contact with the lead wall of the pipe itself, dramatically reducing the amount of metal that could leach into the supply. Archaeological evidence powerfully supports this. Excavated sections of Roman lead pipe often reveal a thick, calcified interior, sometimes reducing the functional diameter of the pipe by half. For the water flowing through the center, it was essentially traveling through a stone pipe lined with lead, not the other way around. This protective mechanism, however, was not universal. Its effectiveness depended entirely on the specific chemistry of the local water supply. A city or neighborhood fed by a hard water aqueduct would have enjoyed this natural filtration. But what about places with soft, acidic water? Water that lacked those protective minerals would have been far more aggressive, actively dissolving lead from the pipe walls and carrying it directly to the consumer. This creates a patchwork of risk across the empire. A citizen in a hard water district might have consumed relatively safe water, while another in a soft water area, perhaps using a local spring source, could have been exposed to steadily increasing doses of the toxin. The risk was also highest when pipes were new, before the protective sinter layer had time to form, and in sections where water was allowed to sit stagnant for long periods, such as in the long lead service pipes running into private homes. The danger, therefore, wasn't a single, empire-wide catastrophe, but a variable and insidious threat that depended heavily on local geography and individual plumbing circumstances. To move beyond theory and into the realm of physical evidence, scientists have turned to a direct source, the bones of the Romans themselves. Our skeletal system acts as a long-term storage site for heavy metals like lead, incorporating them into the mineral matrix of our bones over a lifetime. By analyzing the lead isotopes found in ancient Roman skeletons from various burial sites across the empire, researchers can get a quantitative measure of a person's lifetime exposure. The results of these bioarchaeological studies are revealing, yet again, a nuanced picture. They consistently show that Romans, particularly those from urban centers and from the wealthier, lead-using classes, had lead levels significantly higher than those found in pre-Roman populations. For example, analyses of skeletons from Roman era Britain show lead concentrations several times higher than in Iron Age Britons. This confirms that lead was indeed entering their bodies systemically. However, and this is the critical point, these levels are often not as catastrophically high as some dramatic theories of mass poisoning have suggested. They typically do not reach the acute toxicity thresholds associated with widespread, obvious epidemics of lead-induced illness. What the bone evidence suggests is not a population in the throes of a massive poisoning event, but one living with a chronic, elevated background level of lead exposure, a silent, low-grade burden that would have varied greatly from person to person based on their diet, wealth, and local water source. This complex body of evidence has, quite naturally, split modern historians and scientists into two broad camps. On one side are those who argue that lead poisoning was a significant contributing factor in the decline of the Roman Empire, particularly its ruling elite. Proponents of this viewpoint to the historical descriptions of aristocratic ailments, infertility, and erratic behavior among some emperors. They argue that even moderate, chronic exposure could have caused a gradual cognitive decline, reducing the decision-making capabilities of the Senate and the imperial court. They suggest that lead's subtle effects, increased aggression, irritability, and impaired judgment, could have worsened the political instability that plagued the later empire. For them, lead was a slow-acting poison that eroded the very mental faculties required to govern a complex state, a hidden weakness that made the empire more vulnerable to its external crises. On the other side of the debate, a larger contingent of scholars urges caution, viewing the lead poison theory as an oversimplification of Rome's monumental collapse. These historians and scientists argue that while lead exposure was certainly unhealthy and undoubtedly caused suffering for some individuals, there is simply not enough evidence to support it as a primary or even major cause for the empire's fall. They emphasize that the empire's decline was a sprawling process centuries in the making, driven by an overwhelming confluence of factors: relentless political corruption and civil war, crippling economic inflation and devaluation of currency, the constant pressure of mass migrations and invasions on its vast frontiers, and a series of devastating plagues that killed millions. From this perspective, blaming lead is a form of historical reductionism, latching onto a single, catchy explanation for an event of incomprehensible complexity. They point out that the Eastern Roman Empire, centered in Constantinople, used the same lead plumbing technology for another 1,000 years after the West fell, and while it certainly faced its own challenges, it did not succumb to the same fate, suggesting that political, military, and economic structures were far more decisive. The most balanced conclusion, then, lies not in choosing one side over the other, but in understanding that lead exposure was likely one thread in a much larger, tangled web of decline, a persistent stressor that may have weakened the fabric of Roman society, making it just that much less resilient when the great crises finally arrived. Keeping this sprawling network functioning for centuries required more than just brilliant initial construction. It demanded a culture of continuous and resourceful maintenance. Imagine the challenge: a web of metal pipes buried deep beneath a bustling, ever-changing city, subject to constant, invisible stresses. The ground itself was a restless adversary. As buildings were erected, demolished, and rebuilt over generations, the earth would settle and shift. This ground movement could put immense strain on a rigid pipe, potentially cracking a soldered seam or even crushing the soft lead itself if a heavy foundation stone settled directly on top of it. Then, there was the constant vibration from the rumbling of heavy carts on the cobbled streets above, a relentless percussion that could, over many decades, gradually fatigue the metal at its weakest point. And of course, new construction was a perpetual hazard. A crew digging foundations for a new temple or a wealthy patron's villa might accidentally strike a buried main with a pickaxe, causing an immediate and dramatic geyser that would flood a worksite and deprive an entire neighborhood of its water supply. The system, for all its durability, was not immune to the chaotic, living environment of the city it served. One of the most predictable and fascinating maintenance challenges was the gradual accumulation of mineral deposits inside the pipes themselves. While we've discussed how the hard water's center layer actually protected the water from lead contamination, for the Roman maintenance crews, this same process was a major operational headache. That protective crust of calcium carbonate wasn't static. It grew thicker with every passing year, slowly but surely constricting the pipe's internal diameter. You can think of it like the hardening of arteries. A pipe that started with an opening as wide as a man's fist could, over 50 or 100 years, be reduced to a narrow channel no wider than a finger. This dramatically reduced water pressure and volume at the far end of the line. A public fountain that once produced a proud, arching jet might dwindle to a feeble trickle, a clear sign to the authorities that a section of pipe needed urgent attention. This was a slow-motion crisis, a gradual throttling of the city's lifeblood that required proactive management to prevent entire districts from slowly running dry. When a problem was identified, whether a sudden rupture or a chronic flow restriction, the Roman plumber's response was impressively systematic. His first task was always to locate and isolate the damaged section. This is where the network's clever design, with its bronze stopcocks at key junction points, proved its worth. An official from the water administration could order a specific valve closed, cutting off the flow to the affected branch and allowing repairs to begin without shutting down the entire aqueduct. Then, the laborious work of excavation started, digging down through the packed earth and stone protective casings to expose the faulty pipe. Once the damaged section was visible, the repair technique was a direct extension of the original manufacturing process. Using heavy shears or a saw, the plumberius would cut out the compromised piece of pipe. If the issue was a blockage, he might simply cut out a small window to chisel away the rock-hard cinder deposits before soldering a patch back over the hole. For a cracked or crushed section, he would remove the entire damaged length. The real artistry came in splicing in the replacement. The plumber would prepare a new section of pipe, manufactured to the correct diameter in his workshop, and fit it into the gap. He would then employ the same socket and pour technique used in the initial installation. He built a clay dam around the two new joints and pour molten lead to form solid, watertight collars that bonded the new piece seamlessly to the old. This approach highlights one of the system's greatest strengths, its repairability. The Romans weren't just building a monument, they were building a maintainable utility. The use of a single, easily worked material like lead meant that repairs could be performed indefinitely. A pipe from the time of Augustus could be patched with lead from the reign of Constantine, and then repaired again in the medieval period, all using fundamentally the same technique. This modularity granted the network a form of immortality, allowing it to evolve and persist long after the central authority that created it had faded away. The responsibility for keeping this vital infrastructure running was a shared one, split between public duty and private interest. At the highest level, the water system was overseen by a senior senator, the curator aquarum, who commanded a staff of architects, engineers, and a dedicated force of public slaves. This team was responsible for the grand, city-wide infrastructure, the aqueducts themselves, the main distribution casella, and the large bore pipes that ran beneath the public streets. They conducted regular inspections, authorized major repairs, and allocated water rights. Their work was essential for the common good, ensuring that the public baths, fountains, and sewers, the foundations of urban health and social order, remained functional. However, the moment a pipe branched off from the public main and passed through a property wall, responsibility shifted. The maintenance of that private service line, the fistula, fell squarely on the homeowner. This created a stark divide in the quality of service. A wealthy aristocrat would hire skilled plumberiae to promptly fix any leaks or blockages in his villa, ensuring his private baths and fountains never faltered. A poorer landlord of a crowded insula or apartment block might neglect a failing pipe for years, leaving his tenants to rely entirely on distant public fountains. This patchwork of public and private upkeep meant that while the core network could be maintained for centuries, the experience of the individual Roman with running water was profoundly unequal, a direct reflection of their social and economic standing in the society the pipes helped to shape. This intricate city-spanning network of lead pipes paints a picture of universal access, but the reality on the ground was starkly different. The Roman water system was a powerful engine of social stratification, where the privilege of a private connection was a luxury reserved for the very few, creating a clear hydrological divide between the wealthy elite and the common citizen. For the rich, water was a private convenience. For the masses, it was a public chore. Step inside the spacious, airy villa of a Roman senator, and you'd find water treated as a personal amenity. Here, a private lead pipe, known as a fistula, would branch off from the public main beneath the street, secured with a heavy, official bronze seal to prevent unauthorized tapping. This pipe represented a costly license granted by the emperor or the water commissioner himself. It was a tangible sign of imperial favor and immense personal wealth. This private line would snake through the villa's foundations, emerging in a variety of opulent settings. It might feed a marble fountain in the central courtyard, its gentle splash providing a constant soundtrack of affluence. It would run directly into the private baths, filling heated pools without the owner ever having to leave his property. Most impressively, it could supply a kitchen with a constant flow for cooking and cleaning, and even feed a latrine with a continuous stream to flush waste into the city's sewers. This wasn't just about comfort, it was about control. the wealthy Roman could command water on demand, a miracle of engineering that removed the drudgery of collection from daily life and turned a basic necessity into a display of status. The archaeological evidence from places like Pompeii brings this elite experience vividly to life. The House of the Vetii, owned by two wealthy freedmen, showcases a remarkably complex and extensive private water system. Lead pipes are everywhere, embedded in the walls and under the floors. They feed multiple ornate fountains in its lush gardens, each designed for visual delight rather than mere function. They supply a sophisticated bathing suite and even powered a series of tiny, whimsical fountains in the form of stone masks and statues. The quality of the plumbing here is masterful. The pipes are of a substantial diameter, the soldered seams are neat and professional, and the system includes bronze stopcocks, allowing the owners to control the flow to different parts of the house. This was a hydraulic machine for living, a network designed for pleasure, hygiene, and ostentatious display, all made possible by the craftsman's skill and the owner's deep pockets. Now, cross the threshold into the world of the common Roman, and the picture transforms completely. The vast majority of the city's population, perhaps 90% or more, lived in cramped, multi-story apartment blocks called insulae. For these families, the concept of running water in their home was as fantastical as a flight to the moon. They had no private connection, no lead pipe bringing the empire's bounty to their doorstep. Their entire water supply depended on a relentless daily routine centered on the public fountain. These fountains, fed by dedicated lead mains, were the true lifelines of the common people, strategically placed at major street intersections and in neighborhood squares. Here, from dawn until dusk, a constant stream of residents, predominantly women and slaves, would gather. They came with heavy clay jars and buckets, waiting in line to collect all the water needed for the day's drinking, cooking, and washing. This was not a quick errand. It was a time-consuming, physically demanding chore that shaped the daily rhythm of life. The social atmosphere at the fountain was likely a mix of gossip, camaraderie, and tension, a vital public space where news was exchanged and community ties were forged, but it was a necessity, not a choice. The contrast in infrastructure between the wealthy villa and the common insula is glaring. While the villa had pipes woven into its very fabric, the insula was, hydraulically speaking, a desert. Excavations of these buildings reveal almost no internal plumbing. There were no pipes running up the walls to supply upper-story apartments. At best, a ground floor shop might have a small, illegal tap off a nearby main, but for everyone else, every drop of water had to be carried upstairs by hand. This fundamental lack shaped their entire domestic reality. Without a constant water supply, sophisticated sanitation was impossible. Instead of private latrines, residents relied on public toilets or simply used chamber pots that were emptied into open cesspits or dangerously tossed into the street from upper windows. The sounds and smells of this existence were a world away from the perfumed, fountain-cooled air of the senator's villa. This disparity highlights a profound truth about Roman society. The magnificent water system, while a public good, primarily served to accentuate the gulf between the haves and the have-nots. It provided a basic survival level for the masses through public fountains, while simultaneously enabling a level of private luxury for the elite that was unimaginable to the rest. The lead pipe, therefore, was more than a piece of technology. It was a social filter, determining not just how you got your water, but the very quality of your life in the ancient city. One of the most thrilling ways to connect with this ancient technology is to witness its remains firsthand, emerging from the earth after 2,000 years. The archaeological discoveries of Roman lead pipes offer us tangible, physical proof of the system's incredible scope and durability. No site provides a more vivid snapshot than Pompeii and its neighbor, Herculaneum, both frozen in a single, catastrophic day by the eruption of Mount Vesuvius in 79 CE. In Pompeii, the volcanic ash and pumice that buried the city acted as a perfect preservative, sealing the urban landscape in a time capsule. As archaeologists carefully excavate the streets, they frequently uncover the lead pipe network exactly as it was on that fateful August day. You can stand on a Pompeian street today and see the pipes running along the sides of buildings, entering the walls of wealthy homes and feeding public fountains. In the house of the Vetii, the pipes are still in place, ready to supply water to its elegant courtyard fountains and private baths. At Herculaneum, the preservation is even more dramatic. The city was engulfed by superheated volcanic mud that hardened into a rock-like substance, sealing everything in an airtight tomb. This environment has preserved organic materials like wood and even food, and it has saved the lead pipes in a state of near-perfect condition, often with their original shapes and soldered seams completely intact. Walking through these cities, you are not looking at a reconstruction. You are seeing the actual, physical infrastructure of Roman daily life. But not all pipes are found in such dramatic circumstances. Across the former empire, from the deserts of North Africa to the rainy fields of Britain, lead pipes are constantly being uncovered during modern construction projects and archaeological digs. In the city of Rome itself, anytime a new subway line is dug or a building's foundations are laid, there is a high probability of striking an ancient lead water main. These urban finds are often fragmentary, crushed by centuries of subsequent construction, but they are no less informative. In waterlogged environments, such as the remains of Roman London buried deep in the damp soil along the River Thames, the lack of oxygen can preserve metal wonderfully. Pipes pulled from such context can retain their original surface, allowing scientists to analyze tool marks and even microscopic residues. Each of these discoveries, whether from a volcanic tomb or a muddy riverbank, adds another piece to the puzzle, helping us map the incredible extent of this standardized technology. A pipe found in a remote fort in Germany shares the same basic design and construction techniques as one found in a lavish villa in Italy, proving that the Roman approach to water distribution was a truly imperial, unified system. One of the most exciting aspects for archaeologists when they unearth a pipe is the possibility of finding a stamp. The Romans frequently impressed inscriptions into the soft lead of their pipes before they were installed. These stamps are like tiny historical archives, offering a wealth of information. Very often, they bear the name of the reigning emperor, such as Imp Quis Domitiani of Germanici, which translates to Emperor Caesar Domitian Augustus Germanicus. This provides an incredibly precise dating tool. If a pipe stamped with Domitian's name is found in a layer of excavation, we know that layer must date from his reign between 81 and 96 CE. Other stamps reveal the owner of the pipe, especially for private connections. A stamp might read, "See Eoli Philerotes," indicating the pipe belonged to a man named Gaius Julius Phileros. This tells us not just about the water system, but about social history, showing which wealthy citizens could afford this luxury. Some stamps even name the manufacturer or the workshop, the plumbarius who made the pipe, like Officina Fabri Fecit or Workshop of Faber made this. This was a form of quality control and commercial branding, holding the craftsman accountable for his work. Beyond the stamps, the physical fragments of the pipes themselves are a rich source of information about Roman manufacturing technique. By examining a broken cross-section, archaeologists can measure the exact thickness of the pipe wall, revealing the skill of the plumber in hammering his sheet to a perfect consistency. The long, welded seam is a particular focus of study. A clean, smooth, barely visible seam indicates a master plumbarius who expertly wiped his joint, while a lumpy, irregular seam suggests a less experienced hand. Analysis of the solder used in joints can reveal its precise alloy composition, showing the ratio of lead to tin and providing clues about trade and metallurgical knowledge. Even the simple dents and scratches on the exterior of a pipe can tell a story. A deep gouge might be the mark of a clumsy shovel during its original installation, while a pattern of abrasion could show where it rubbed against a stone support for decades. These silent artifacts speak volumes about the hands that made them and the world they served. Perhaps the most significant contribution of this archaeological evidence is how it allows us to literally map the ancient water network. When pipes are found in situ, that is, in their original position, they chart the course of the water's journey through a city. A large diameter pipe discovered under a main street clearly marks a primary public main. A smaller pipe branching off from it and disappearing through the foundation of a house shows the route of a private supply. By plotting all these finds on a map, archaeologists can begin to reconstruct the entire hydraulic system of a Roman town. They can identify where the water entered the city from the aqueduct, trace its path to the central distribution castle, and follow its branching arteries out into the neighborhoods. This work has revealed surprising sophistication. For instance, the network was not static, it evolved. Excavations in Ostia, the port of Rome, show how the pipe system was expanded and modified over centuries to accommodate the city's growth. The cumulative testimony of these unearthed pipes, from the grandest main to the humblest service line, provides a definitive physical proof of an achievement that text alone could never fully capture. It shows us an empire connected not just by roads and legions, but by a continuous, flowing stream of water, channeled through the durable, silent, and ever-present veins of lead. Of course, a network of pipes is just a static sculpture without the ability to command the water within it. The true genius of the Roman system wasn't just its ability to deliver water, but its capacity to control it with precision. This mastery was achieved through an array of ingenious bronze fittings, valves, stopcocks, and faucets that transformed a passive conduit into an interactive utility. Imagine being the Aquarius, the water engineer, faced with a major leak in a pipe buried beneath a bustling market street. In a primitive system, you'd have to shut down an entire aqueduct, depriving a whole sector of the city of water just to fix one break. The Romans engineered their way around this nightmare with a simple but revolutionary device, the bronze stopcock. This was the shut-off valve of the ancient world, a crucial piece of technology that brought administrative order to the flowing chaos. At key junction points throughout the network, particularly where a pipe branched off from a main, a heavy, custom-fitted bronze sleeve would be soldered directly into the lead pipe. Inside this sleeve sat a tapered, cylindrical bronze plug, meticulously machined to create a perfect, watertight seal. The plug had a hole drilled straight through its center. When this hole was aligned with the pipe, water flowed freely, but when an attendant inserted a special metal key called a clavis into the square or rectangular head of the plug and gave it a quarter turn, the solid side of the plug would rotate into the path of the water, blocking it completely. With a simple twist of the wrist, a single section of the network could be isolated for repair, while the rest of the city carried on, blissfully unaware of the maintenance happening just beneath their feet. Beyond these critical stopcocks, the Romans also brought the point of control directly to the user with the invention of the faucet. In the public baths and the homes of the wealthy, water didn't just flow incessantly from a spout, it could be summoned and stopped at will. The basic Roman faucet, or epistomium, operated on the same principle as the stopcock, but on a smaller, more personal scale. It was typically a compact, beautifully cast bronze fixture, often decorated with animal heads or mythological figures, with the water spout forming the creature's mouth. The bather or homeowner would turn a handle, rotating an internal plug to start or stop the flow. This wasn't merely a convenience, it was a profound leap in resource management and hygiene. In a bath complex, attendants could control the filling of pools and tanks precisely. In a private kitchen, a faucet prevented the constant waste of water, a valuable and measured commodity. The very presence of a faucet implies a society that thinks about water not as an uncontrollable force of nature, but as a managed resource, a utility that can be commanded with a simple, mechanical gesture. Perhaps most impressively, there is compelling archaeological and literary evidence that Roman engineers developed even more sophisticated valves to solve complex hydraulic problems. One such device was a precursor to the modern pressure-reducing valve. Some aqueducts descending from great heights could generate tremendous pressure in their lower sections, enough to potentially damage pipes and fittings or create dangerous, uncontrollable jets at public fountain. To mitigate this, engineers appear to have used a system of sequential constriction. They would install a series of specially designed bronze valves along a pipeline, each one featuring a gradually smaller aperture. As water was forced through these progressively narrower openings, its velocity would increase, but its downstream pressure would drop significantly, a process governed by the Venturi effect, a principle they understood empirically long before it was formally defined. Another potential innovation was a simple check valve. a fitting that would allow water to flow in only one direction, preventing backflow and contamination of the main supply from a private branch line. While the evidence for these is more circumstantial, their existence is entirely plausible given the Romans' demonstrable, practical understanding of hydraulics. They weren't just moving water, they were taming it, engineering its behavior to ensure a stable, safe, and efficient delivery from the reservoir to the basin. The craftsmanship of these metal fittings reveals a culture that took immense pride in its infrastructure, even in the parts that were mostly hidden from view. Unlike the utilitarian lead pipes, these bronze valves and faucets were often objects of beauty. Excavated examples show exquisite detail, with bodies cast in the shapes of dolphins, wolves, or satyrs, and handles fashioned into intricate shells or leaves. This aesthetic attention tells us that for the Romans, plumbing was not a grubby, secretive trade, but a noble art that married functionality with civic pride. The bronze itself was a deliberate choice, strong, resistant to corrosion, and easy to cast with precision. The survival of so many of these pieces, still operable after 2 millennia, is a testament to their quality. Together, this suite of technologies, from the humble stopcock to the ornate faucet, form the control network for the entire water system. They were the synapses in the city's brain, allowing engineers to manage flow, pressure, and distribution with a level of sophistication that would not be seen again in the West for over 1,000 years. This wasn't just plumbing, it was the birth of fluid dynamics as an applied science, demonstrating that the Romans understood their hydraulic network not as a passive sculpture, but as a dynamic, living system that required intelligence and command at every turn. The echoes of the Roman plumbarius did not simply fade into silence with the fall of the Western Empire. Instead, they rumbled underground for centuries, a dormant legacy waiting to be rediscovered. As the centralized Roman administration crumbled, the intricate knowledge required to maintain the vast aqueducts and lead pipe networks gradually fragmented and was lost in many regions. Without the imperial engineers and the organized guilds of craftsmen, the sophisticated understanding of gradients, water pressure, and soldering techniques slipped from common practice. In the early medieval period, across much of Europe, the magnificent Roman water systems fell into disrepair. Aqueduct channels cracked and clogged, and lead pipes were often scavenged for other uses, their metal melted down for roofing or, grimly, for bullets in countless wars. For hundreds of years, the water supply for most towns reverted to far more primitive methods: local wells, cisterns, and nearby rivers, with all the attendant risks of contamination and scarcity that the Romans had once overcome. The very concept of a pressurized, closed-pipe water distribution system became a half-remembered legend, a ghost of a more advanced age, yet the physical infrastructure itself was so robust that it refused to disappear entirely. In a fascinating twist of history, many Roman lead pipes remained in use long after their creators were gone. In cities like Rome itself, and in places like Segovia in Spain, the decaying empire's plumbing was patched and maintained in a diminished form by local communities for generations. Medieval monks, recognizing the value of a reliable water source for their monasteries, sometimes became the unlikely heirs to this technology, carefully preserving and repairing sections of Roman piping they found on their land. But this was mere custodianship, not innovation. The true reawakening of hydraulic engineering had to wait for the intellectual and cultural explosion of the Renaissance. It was during this era that European scholars, artists, and engineers, fueled by a renewed fascination with classical antiquity, began to systematically study the physical ruins of the Roman world. They saw the broken aqueducts not as piles of old stone, but as textbooks of lost engineering. They examined the lead pipes that were occasionally unearthed, marveling at their workmanship. The single most important figure in this revival was the Renaissance architect Leon Battista Alberti. In the 15th century, he undertook a meticulous survey of the ancient Roman aqueducts, publishing his findings in his seminal work, De Reedificatoria, on the art of building. Alberti didn't just describe the ruins, he analyzed their principles. He understood and explained the critical importance of the constant, gentle gradient, the use of sedimentation tanks, and the robust construction methods. His work became a blueprint for a new generation of engineers, effectively translating the empirical knowledge of the Romans into a formalized body of principles that could be applied anew. This rediscovery coincided perfectly with the growing wealth and ambition of Renaissance city-states and monarchs, who saw advanced waterworks as both a practical necessity and a powerful symbol of their modern, enlightened rule, worthy of comparison to the ancient Caesars. When these early modern engineers began constructing their own water systems, they quite naturally turned to the material and methods that the Romans had proven over centuries. The basic principles of pipe fabrication demonstrated a remarkable persistence. The Renaissance plumber, much like his Roman predecessor, would melt lead pigs in a furnace, pour the metal onto a flat surface to create a sheet, and then skillfully hammer that sheet around a cylindrical iron mandrel to form a pipe. The technique for sealing the long seam was also directly inherited. The wipe joint, where a craftsman uses a hot soldering iron and a damp cloth to fuse the seam, is virtually identical to the method used by a Roman plumberius. This wasn't just a coincidence, it was the most logical and effective way to work with the material, and the knowledge had been passed down in an unbroken, if tenuous, chain of craft tradition. Perhaps the most direct and tangible line from ancient Rome to the modern world is found not in a pipe, but in a word. The Latin plumbum gives us our English word, plumbing. The man who worked with it was the plumberius, which evolved directly into plumber. Even the chemical symbol for lead, Pb, is a permanent abbreviation of that ancient Roman name, etched onto the periodic table for all time. This linguistic thread is a powerful reminder that the entire trade, its very identity, is rooted in the workshops of the Roman Empire. For centuries after the Renaissance, the plumber's primary material remained lead. When London began building its first extensive water supply network in the 17th and 18th centuries, it was largely constructed from lead pipes. The same was true for Paris and many other major European and American cities well into the 19th century. The profound shift, of course, came with the dawning understanding of lead's toxicity, a danger the Romans had glimpsed but could never fully prove. The very public health crisis that the elaborate Roman water system was designed to prevent the spread of waterborne disease was being inadvertently worsened by the material of the pipes themselves in the modern era. This led to a slow, costly, and monumental effort to replace lead service lines with safer alternatives like iron, steel, and eventually copper and plastic throughout the 20th and 21st centuries. This great replacement project stands as one of the largest public works undertakings in history, a direct and costly consequence of an ancient technological choice. Yet, even as we move away from the material, the fundamental principles of the craft remain. The concepts of pressurized systems, gravity-fed gradients, shut-off valves, and watertight solder joints are all part of the Roman inheritance. Today's plumber, with his modern tools and materials, is the direct professional descendant of the Roman craftsman who wrapped his lead sheet around an iron rod. The trade he practices, essential for preventing disease and enabling modern urban life, was given its name, its foundational techniques, and its original purpose 2,000 years ago when the first plumberius sealed a joint and sent water flowing into the heart of an eternal city. The story of Roman lead pipes isn't confined to the streets of Pompeii or the villas of senators. Its most lasting legacy may be written in the most remote and pristine ice of the planet. To truly grasp the industrial might of Rome, we must journey thousands of miles from the Mediterranean to the vast, silent ice sheets of Greenland. Here, scientists have drilled deep into the glaciers, extracting long, cylindrical ice cores that act as a frozen archive of Earth's ancient atmosphere. Layer by layer, year by year, snowfall trapped tiny bubbles of air and dust, preserving a chemical record of our planet's history. When researchers analyze these cores for lead contamination, they find something astonishing. The graphs show a dramatic, sustained spike in atmospheric lead pollution that begins around the time Rome rose to power, peaks during the height of the empire, and then falls away sharply after its collapse in Western Europe. This is not a minor fluctuation. At its peak, lead pollution in the atmosphere reached levels that would not be seen again until the Industrial Revolution nearly 1,500 years later. This Greenland ice acts as a global barometer for heavy metal pollution, and the signal from the Roman smelting operations in Spain and Britain was so powerful that it traveled across continents and settled on the polar ice cap. It's a humbling piece of evidence that demonstrates the Roman metallurgical enterprise was not just a local industry, but a force of nature with a genuinely planetary reach. This pollution had a clear and relentless source, the smelting furnace. Every time a Roman furnace was fired up to extract lead from galena ore, it released a plume of toxic vapor into the sky. The process was inherently dirty. The lead sulfide in the ore, when heated with charcoal, would not only produce liquid lead, but also a gas sulfur dioxide, and most significantly for our ice cores, vast quantities of lead particles themselves. These microscopic particles of lead, along with other metals like copper and arsenic that were often present in the ore, would be carried high into the atmosphere by the heat of the furnace. Once aloft, they could be transported for thousands of miles by global wind patterns before eventually falling back to Earth in rainfall or dust, some of it making the incredible journey all the way to the Arctic. The sheer scale of this output is what's so difficult to comprehend. We're not talking about a few hundred furnaces. We're talking about an industry that ran continuously for centuries. In major mining districts like Rio Tinto in Spain, the landscape was dotted with smelting sites, each one billowing its own contribution into the air day after day, year after year. The cumulative effect created a metallic smog that blanketed the northern hemisphere, a silent, invisible testament to an empire's insatiable demand for metal. The environmental cost, however, was felt most acutely right at the source. The mining regions themselves were transformed into brutal lunar landscapes. To fuel the endless cycles of smelting, the Romans needed an almost unimaginable amount of charcoal. Creating that charcoal required wood, and lots of it. This led to systematic and widespread deforestation around major mining centers. Hillsides that were once covered in forests were stripped bare to feed the insatiable hunger of the furnaces. We can see evidence of this ecological devastation in pollen records from lake sediments in Spain, which show a dramatic decline in tree pollen and a corresponding rise in pollen from hardy shrubs and grasses that thrive in deforested, eroded soils. The land itself began to waste away. Without tree roots to hold the soil in place, the exposed earth was vulnerable to erosion. Winter rains would wash the barren hillsides down into the valleys, choking rivers with silt and creating floods that ruined agricultural land downstream. The mining process itself was equally destructive. Miners would often use a technique called hushing, where they dammed streams to create large reservoirs of water, which they would then release in a sudden, powerful wave to scour away soil and bedrock, exposing the ore beneath. This violent method would tear entire hillsides apart, leaving behind a scarred wasteland of gullies and rubble. This industrial assault created a cascade of secondary consequences that poisoned the local environment for generations. The waste from the smelting process, the slag, was often simply dumped in massive piles near the furnaces. This slag, still rich in lead, arsenic, and other heavy metals, would be weathered by rain. As water percolated through these toxic heaps, it would leach out the metals and carry them into nearby streams and groundwater, effectively creating long-term, slow-moving poison factories. Rivers downstream from mining districts would have been lifeless, their waters contaminated, and their beds coated with metallic silt. The impact on local ecosystems and human health in these regions must have been catastrophic, though it's a story largely lost to the historical record, overshadowed by the economic benefits the mines brought to Rome. The local tribes who lived near these mines, often forced to work in them, would have borne the brunt of this pollution, suffering from the same respiratory and neurological ailments that Vitruvius observed in the lead workers, but on a community-wide scale. The grandeur of the Roman water system, with its elegant lead pipes bringing fresh water to 1 million people, was ultimately built on a foundation of localized environmental ruin and human suffering, a stark reminder that every technological leap forward can cast a long and often hidden shadow. This deeply ingrained image of a civilization slowly poisoning itself into oblivion is one of history's most compelling and persistent narratives. we can easily picture a ruling class growing increasingly erratic, their judgment clouded by a constant, low-level toxin, while the general populace becomes infertile and weak. It's a story that makes a certain dark, poetic sense, framing the fall of Rome as a kind of tragic flaw, an internal rot. But when we hold this popular theory up to the harsh light of modern scholarship, the picture becomes far more complicated, and the role of lead shifts from a central villain to a troubling but secondary character in a much larger drama. The truth is, the decline and fall of the Roman Empire was not a single-event catastrophe. It was a slow-motion unraveling caused by a perfect storm of interconnected crises, where lead poisoning was at best a contributing stressor, not the primary cause. First, let's address the scale of the exposure itself. While the evidence from Greenland ice cores confirms massive lead pollution from Roman smelting, and skeletal analyses show elevated lead levels in urban remains, these levels generally fall short of what toxicologists would classify as acute epidemic-level poisoning. The key factor, as we've discussed, was the prevalence of hard water. In cities like Rome itself, fed by mineral-rich aqueducts, the protective sinter lining inside the pipes would have drastically reduced the amount of lead leaching into the daily water supply for a significant portion of the population. The risk was undoubtedly higher for the wealthy elite, who not only had private lead pipes, but also consumed wine sweetened with defrutum, a syrup reduced in lead line pots, and ate from lead alloy tableware. They were likely exposed to a cumulative cocktail of lead sources. However, even for this privileged class, the effects would have been varied and chronic, manifesting as things like general fatigue, digestive issues, or mood swings, rather than a uniform descent into madness and sterility. The historical record itself is telling. If lead poisoning were as rampant and debilitating as the myth suggests, we would expect to find clearer, more consistent descriptions of its distinctive symptoms, like the wrist drop paralysis common in lead workers in the extensive medical and historical texts of the period. Instead, we get scattered observations, like those from Vitruvius and Juvenal, which point to a recognized hazard but not a society-wide plague. Furthermore, the timeline of Roman history simply doesn't align with the poisoning narrative. The widespread use of lead pipes and utensils was not a late imperial innovation. It was a practice that began during the Republic and continued for centuries through Rome's most stable and expansionist periods, the era of the Pax Romana. If lead was the primary culprit for the empire's collapse, why did it take over 400 years for the effects to fully manifest? More strikingly, the Eastern Roman Empire, centered in Constantinople, continued to use lead pipes and the same basic technologies for another 1,000 years after the Western Empire fell in the 5th century. The Eastern Empire faced its own challenges and eventual decline, but it sustained a sophisticated, powerful state for a millennium, clearly demonstrating that the presence of lead plumbing was not an automatic death sentence for a complex civilization. This single fact is perhaps the most powerful argument against the simplistic poisoning theory. So if lead wasn't the star of the show, what forces were truly driving the collapse? Historians point to a confluence of monumental problems that overwhelmed the Roman state's ability to cope. Politically, the empire descended into a vicious cycle of instability. The 3rd century, for example, is often called the crisis of the 3rd century, a 50-year period where the empire nearly disintegrated under a relentless series of civil wars, coups, and short-lived emperors, many of them assassinated by their own troop. This created a culture of chronic insecurity where military strength often trumped administrative competence, and long-term planning became impossible. Economically, the empire was being bled dry. Constant warfare and a massive, bloated bureaucracy were incredibly expensive. To pay for it all, emperors repeatedly debased the silver currency, melting down older coins and reminting them with less precious metal. This led to runaway inflation, shattering public trust in the monetary system and crippling long-distance trade. A price edict from Emperor Diocletian in 301 CE vividly illustrates this desperation, attempting to fix the prices of thousands of goods and services by imperial decree, a futile effort to command an economy that was spiraling out of control. At the same time, immense external pressures were hammering the empire's borders. the once formidable Roman legions found themselves stretched thin, defending a frontier thousands of miles long against increasingly powerful and organized groups like the Goths, Vandals, and Huns. These weren't just disorganized raiders, they were often entire peoples on the move, pushed by their own pressures from further east. The Roman military machine, designed for conquest and counterinsurgency, struggled to adapt to this new reality of persistent, large-scale invasion. Compounding all of this were devastating pandemics, such as the Antonine Plague and the Plague of Cyprian, which swept through the empire, killing millions and depopulating entire regions, which in turn reduced the tax base and the pool of military recruits. This created a vicious cycle. Fewer people meant less wealth and fewer soldiers, which meant a weaker defense, which led to more invasions and further decline. Thinking critically about the fall of Rome is a lesson in resisting the allure of the single, simple answer. Human history, especially the fate of something as vast and complex as an empire, is rarely so neat. The lead poisoning theory is a classic example of what historians call monocausality, the attempt to explain a hugely complicated event with one primary cause. It's a satisfying narrative because it's easy to grasp and carries a moral lesson about the hidden dangers of technology, but reality is almost always messier. It's more accurate to view lead exposure not as a single arrow that struck Rome down, but as one of many weights placed on a scale that was already tipping. It may have exacerbated existing social and health problems. It may have weakened the resilience of certain segments of the population, but it did not, on its own, cause the collapse. The true story is one of a political system that could no longer govern itself, an economy that broke down, and a military that could no longer secure its borders against overwhelming odds. By looking past the seductive myth, we don't diminish the Roman achievement or its tragedy. We actually appreciate it more fully, understanding that their world, like our own, was a fragile construct, vulnerable not to a single poison, but to a cascade of failures. But how can we truly grasp the skill of the Roman plumber without feeling the heat of the furnace or the weight of the hammer? This is where the fascinating field of experimental archaeology takes center stage, transforming historical theory into tangible, hands-on experience. Modern historians, working alongside skilled blacksmiths and metalworkers, have stepped back in time by attempting to recreate Roman lead pipes using only the tools and methods described in ancient texts and unearthed from archaeological sites. Their workshops become living laboratories, where the written word and the excavated artifact are tested against the unyielding reality of fire, metal, and muscle. The first major hurdle they face is sourcing the material itself. The Romans used a specific type of lead, often with its own unique impurities from mines like those in Spain. Modern, highly refined lead behaves slightly differently, so experimenters often seek out antique lead from old roofing or plumbing to get as close as possible to the authentic working properties. Then comes the challenge of the tools, forging a heavy iron mandrel, crafting a hammer with the correct weight and face, and even making the simple yet crucial iron shears requires a deep understanding of pre-industrial blacksmithing. Each tool must be perfect because in the hands of a master, the tool is an extension of the body, and any imperfection is magnified in the final product. One of the most illuminating aspects of these experiments is the sheer physical labor involved, something that is easy to underestimate when looking at a finished pipe in a museum case. The process begins with reducing a heavy lead pig to a workable state, a task that alone requires significant strength. Then comes the pouring and hammering of the sheet. Modern practitioners quickly learn that achieving a perfectly uniform thickness is not a matter of a few random strikes. It demands a rhythmic, systematic hammering technique, a constant, careful inspection of the metal surface, and an intuitive sense for how the lead moves and spreads under the hammer. Any lapse in concentration, any area struck too hard or too softly, results in a weak spot that could doom the entire length of pipe. The goal is a sheet that is not just flat, but consistently thick, a canvas without a single flaw. This stage alone can take hours for a single sheet, revealing that Roman pipe making was not a quick process, but a deliberate and time-consuming craft where patience was as important as power. However, the ultimate test of skill, the moment that separates a successful replication from a failed experiment, is mastering the wipe joint. Modern metalworkers, even those with years of experience, often find this to be the most difficult technique to perfect. It's a delicate ballet of heat and pressure that looks deceptively simple in description, but is incredibly difficult to execute. Controlling the temperature of the soldering bolt is the first challenge. It must be hot enough to melt the edges of the seam, but not so hot that it burns through the thin pipe wall. Then comes the critical timing. The craftsman has only a few seconds after applying heat to press and wipe the seam with the damp cloth, forcing the semi-liquid lead to fuse. Too early, and the metal isn't molten enough to bond. Too late, and it has already cooled and solidified, creating a weak, grainy joint. Many first attempts result in a messy, lumpy seam, or worse, a hole burned straight through the pipe. It can take dozens, sometimes hundreds, of attempts to develop the muscle memory and the intuitive feel for the metal's behavior that a Roman plumbarius would have learned through a long apprenticeship. This struggle alone gives us a profound appreciation for the level of expertise embedded in even the most common Roman water pipe. The insights gained from these recreations are invaluable. They move us beyond speculation and provide hard data. We learn that a small team could likely produce a few meters of good quality pipe in a full day's work, giving us a sense of the labor investment required for vast urban projects. By testing the finished replica pipes, we can quantify their effectiveness. Researchers have subjected these handmade pipes to water pressure tests, often finding that a well-executed wipe joint is nearly as strong as the parent metal, capable of withstanding pressures far beyond what the Roman system would have typically generated. This empirical evidence confirms that the Roman methods were not just adequate, they were exceptionally robust. Furthermore, these experiments shed light on the working conditions and the hidden knowledge of the craft. The modern practitioners quickly become aware of the dangers, the risk of lead fumes during melting, the constant threat of burns, and the sheer physical fatigue. They gain an embodied understanding of why a workshop needed to be well ventilated, why certain stances and grips were necessary, and how the rhythm of the work was dictated by the cooling time of the metal. Ultimately, this hands-on approach does more than just validate historical theories. It bridges a 2,000-year gap, allowing us to appreciate Roman engineering ingenuity on a deeply human level. Holding a hand-forged mandrel, feeling the lead sheet slowly wrap around it, and experiencing the satisfying sizzle of a perfectly wiped joint creates a connection to the past that no textbook can provide. It transforms the anonymous Roman craftsman from a vague historical figure into a colleague, a skilled professional whose knowledge was earned through years of practice and passed down through generations. We stop seeing the lead pipe as a simple artifact and start to see it as the product of a living, breathing person with calloused hands, a keen eye, and a profound understanding of their material. This experimental journey brings the ancient craft roaring to life, not as a lost secret, but as a testament to a level of practical, hands-on intelligence that commands our respect and deepens our understanding of the world the Romans built, one carefully crafted pipe at a time. And so our journey through the veins of the Roman Empire reaches its final stop. From the dark, suffocating mines of Hispania to the roaring furnaces of the plumber's workshop, and ultimately into the hidden channels beneath the city's bustling streets, we have traced the incredible life cycle of a technology that shaped a civilization. We've marveled at the ingenuity of the craftsmen who transformed raw, dull ingots into seamless, durable channels using little more than a hammer, a mandrel, and his own profound skill. We've witnessed the sophisticated hydraulic principles that animated this network, a system managed with bronze valves and precise gradients, delivering the lifeblood of an empire with a consistency that would not be matched for over 1,000 years. This was more than mere plumbing. It was a monumental expression of human ambition, a declaration that nature could be commanded and urban life elevated to an unprecedented level of comfort and grandeur. Yet, woven inextricably through this story of triumph is the sobering thread of its legacy. The very same pipes that delivered the water enabling Rome's famous baths, its public health, and its civic beauty also carried a silent, insidious risk, a danger that a few astute observers like Vitruvius noted. but which a society dependent on the technology could not afford to fully confront. Our modern perspective, informed by ice cores from Greenland and chemical analysis of ancient bones, reveals the complex truth. This is not a simple tale of a civilization blindly poisoning itself into ruin, but rather a more nuanced reality of a society living with a persistent, low-level environmental stressor. The debate over Leeds' role in Rome's fall endures, a testament to our desire to find a single, satisfying explanation for a collapse that was, in fact, the result of a perfect storm of political decay, economic crisis, and relentless external pressure. The lead pipes, for all their potential harm, were likely just one crack in a dam that was already buckling under the weight of far greater forces. This enduring contradiction is perhaps the most powerful lesson the Roman lead pipe holds for us today. It stands as a timeless symbol of the double-edged nature of innovation itself, a material that was abundant, malleable, and seemingly perfect for its purpose also harbored a hidden cost that unfolded across generations. The Roman engineers were not foolish. They were brilliant problem solvers working with the best knowledge and materials available to them, creating a system of such resilience that parts of it outlasted the empire that built it. Their story forces us to look at our own world, at the plastics, the chemicals, the digital networks that define our modern existence, and to humbly ask what unintended legacies we might be creating for the future. What brilliant solutions of ours might carry a hidden shadow we cannot yet see. The ghost of the Roman plumbarius is not just in the physical pipes we still dig up, but in the very word plumber and the chemical symbol Pb, a permanent echo of plumbum on the periodic table. Their craft, their ingenuity, and their unwitting dilemma are woven into the fabric of our own civilization. It's a story that compels us to admire human achievement while remaining vigilant about its consequences, to celebrate the engineering marvel without ignoring the complex price tag. If this exploration into the hidden arteries of the ancient world has captivated you, I'd love to hear which Roman mystery we should investigate next. Should we delve into the secrets of their concrete that still stands strong after 2 millennia, or perhaps uncover the truth behind the bizarre rituals of the Mithras cult? Let me know your thoughts in the comments below, and for more journeys deep into the past, be sure to subscribe. Thank you for watching.